Quantization error is a fundamental concept in digital signal processing, data compression, and numerical computation. It describes the difference between an analog signal and its digital representation, essentially a rounding error. This error is crucial for how accurately computers, sensors, and communication systems represent real-world information. Understanding it is essential in fields like audio processing, image compression, and deep learning, where precision affects performance. The physical world is analog, with continuous variations in sound waves, temperature, light, and voltage. Digital systems only store discrete values, requiring sampling and quantization for digitization. Sampling involves measuring the signal's amplitude at regular time intervals. Quantization maps each sampled amplitude to the nearest value within a finite set of digital levels. For example, 127.6 must be rounded to either 127 or 128. The difference between the true value and the rounded value is the quantization error. Quantization is similar to rounding numbers. Rounding 3.67 to 4 results in an error of plus 0.33. The quantization step size, delta, defines the spacing between adjacent digital levels. The maximum quantization error is half of the step size, delta over 2. Smaller step sizes, achieved by increasing bit depth, reduce quantization error, leading to more accurate digital representations. A 4-bit quantizer has 16 distinct levels, leading to noticeable quantization error. A 16-bit quantizer has 65,536 levels, producing a much smaller step size and nearly imperceptible error. This explains why high-quality audio systems use 16-bit or 24-bit depth to minimize quantization noise and achieve cleaner sound. Because quantization error adds small random differences, it can be modeled as noise, often called quantization noise. This noise behaves like an unwanted signal superimposed on the original one, often uniform and random. The mean squared value of this error determines the quantization noise power, which calculates the signal-to-quantization noise ratio, SQ&R. Increasing the number of bits by 1 approximately improves the SQ&R by about 6 dB, providing superior dynamic range and fidelity. To visualize quantization error, imagine plotting a smooth sine wave. The analog version is continuous and fluid. When digitized, it becomes a series of discrete steps that approximate the curve. The vertical difference between the true curve and each step represents the quantization error. If quantization levels are coarse, steps are large, and the waveform looks blocky, resulting in audible distortion or visible artifacts. If the levels are fine, the steps are small, and the output closely follows the original signal. One fascinating technique to mitigate quantization error is dithering, which intentionally adds a small amount of random noise before quantization. While counterintuitive, dithering helps randomize the error so it doesn't correlate with the signal. By introducing randomness, dithering turns structured error into uncorrelated noise, making it less perceptible to human senses. This technique is widely used in digital audio mastering, image compression, and video rendering. Quantization error isn't limited to analog signals. It's also critical in modern artificial intelligence and compression algorithms. In neural networks, quantization reduces model size and computation by representing weights and activations with fewer bits. Converting 32-bit floating point numbers to 8-bit integers speeds up inference, but introduces quantization error. In image and video compression, quantization removes high-frequency details that humans are less sensitive to, balancing quality and file size. Several methods exist to minimize quantization error, depending on the application. One method is to increase bit depth, meaning more bits per sample for finer resolution and smaller step sizes. Another is to use non-uniform quantization, assigning more levels to frequently occurring signal ranges, improving accuracy where it matters most. Applying dithering adds controlled randomness to smooth out correlated errors. Signal scaling normalizes or amplifies the signal before quantization to use the full dynamic range of available levels. Quantization error is often invisible but always present wherever analog data meets digital systems. It determines the precision of sensors, the clarity of sound and images, and the stability of numerical algorithms. Even small rounding errors can accumulate and affect outcomes in sensitive applications like scientific simulations or financial modeling. In essence, quantization error represents the cost of digitization, a price paid for the benefits of compact storage, transmission, and digital manipulation. Understanding it helps engineers design systems that retain as much fidelity as possible while staying practical and efficient. Quantization error is the inevitable result of mapping continuous analog signals to discrete digital values. Though it introduces distortion and noise, its impact can be managed and minimized through techniques like increased bit depth, dithering, and non-uniform quantization. From digital audio to deep learning, the principles behind quantization error shape the accuracy and quality of modern technology. By mastering this concept, engineers and data scientists can strike the perfect balance between precision, performance, and efficiency, ensuring the digital world represents the analog one as faithfully as possible.